mathematical aspect of calorimetry. Thermodynamics is calorimetry, and that's the study of heat transfer. So, first thing we're going to do is start with their units. The System International, or the International System of Units for energy, are joules. Joule, by definition, is related to work. So, work is force times distance. Force is 1 kilogram times 1 meter per second, which is 1 Newton. But we're going to stick with joules. And if we did kinetic energy is 1/2 times the mass velocity squared. Okay, so this is one of our base units right here. Again, you don't have to memorize these. The old unit that was often used was the calorie. And calorie was often used in organic things. We still use it today, modified version, get to that in just a second. And the conversion between calories and joules is 4.184 joules is 1 calorie. And the calorie definition is actually a little easier to deal with. 1 calorie is the energy needed to raise 1 gram of water by 1 degree C. So that's the set point. Now, the fun thing is a nutritional calorie. A nutritional calorie is a capital C calorie, known as a big C calorie, or what it really is 1,000 little calories or kilocalorie. Now, why is this interesting? Well, because you have Coke Zero and you have Pepsi Zero. Are they 0 calories? No, they're not 0 calories. They're big C 0 calories. Because as long as you have under 409 or 500 calories, so little c calories, 499, that rounds to 0. So when they say that they're 0 calorie, they're not little c 0 calorie, they're big C big C calories. So when you're eating that candy bar that's only 240 calories, that's actually 240,000 little c calories. Yeah, I'm still eating the candy bar too. So just letting you know that there is a difference between nutritional calories, which are big C calories or kilocalories, and little c calories. Now, the other thing that throws into energy is kilowatt hour. And the only reason I really point that out is in some of the mastering, which I'm assuming y'all are doing okay with. Nobody has reported any major problems with the online homework, but there are a couple of the kilocalorie problems that kind of sneak in. All right, so let's talk about calorimetry. Calorimetry is the process of measuring the amount of heat involved in a chemical reaction or physical change. There are 2 types of calorimeters. There's the coffee cup calorimeter, which we would work with in lab, which is constant pressure. Then there's the bomb calorimeter, which most people really don't let you play with because it has the word bomb in it for a reason. More about it in just a minute. But it's constant volume. Now, what is going on is what we're really looking at is heat transfer. It's going from one item to another because remember, according to the law of conservation of energy, you can't create energy, you can only convert it back and forth. So when we talk about calorimetry, what we're doing is transferring energy. Now, you do this all the time, you just don't really pay attention to calling it calorimetry, because if you've ever had a really hot drink and you drop a cube of ice in it, what you're doing is you're lowering the temperature via calorimetry. If you leave a spoon in hot tea, then you reach out and grab the spoon, it's hot. So the heat has transferred through. My father for years has put a spoon, and if you don't watch him, he'll put 2 spoons in his hot tea because he wants it to cool down faster. Sometimes he does the ice trick, but usually he just puts spoons in there, okay? Because you're transferring heat out. So let's look at an example of it. And when you go to do the lab, you will actually see we don't use 2 cups. We don't use a stirrer like this, but we use a stirring bar in here. It's kind of like a round little pellet. But we're going to stir, and we're going to, they have a nice cork stopper. We're high tech. We use a piece of cardboard. It actually does really well. If you're trying to transport cold items, I transport cold items all the time south to my mother and sister, and then transfer stuff back. If you take and just instead of just putting it into the cooler, and you don't want ice just to wet it, if you put a towel or newspaper works really, really well. It acts like an insulator. It'll keep it colder longer. So high tech, we're using cardboard, and we've got 1 or 2 styrofoam cups nested together. And so what's actually going on is this is an isolated system. So what happens is the chemical reaction is the system. The water is the surroundings. Surroundings. Okay, this is isolated. And so you keep the system and the surrounded together. And this is constant pressure. Why is it constant pressure? Well, you're doing this in the lab, and unless you're in the middle of a hurricane, these reactions don't take that long, and the temperature isn't going to change. The pressure is not going to change. You hope the temperature changes. The pressure is not going to change. So you're dealing with the atmospheric pressure, so it's not going to change. Okay, on the other hand, here we have constant volume. This is your bomb calorimeter. This, of course, was the coffee cup. And as low tech as it is, it actually works. Now, with the bomb, it's a little more involved. So, what you have is still an insulated container, so still an isolated system. So, what you do is you have water in the bomb calorimeter. You have a stirrer that's going to stir the water. You're going to have the thermometer, which you had over here, that's going to take the temperature. Now, the only difference is this is the bomb part. Okay, so what this is it's a stainless steel, usually stainless steel, but it's a metal container that you screw together and you fill with oxygen gas. Okay, you do this after you put in the sample. So you put in the sample, there's your sample, and then you fill it with oxygen gas. And then this is where you have the ignition wires. Well, what's that mean? Well, it literally is attached to, like on the old cartoons where you saw them, the plunger and it goes boom. Well, it's basically the same effect. What the plunger does in this case is it allows the positive and the negative to connect to the circuit. So that means that you have an ignition because there's a wire here that will ignite the oxygen. You got a lot of oxygen, it's going up. So what happens then is this goes up. That means it's going to burn. And as it burns, it gives off heat or will absorb heat. And the heat goes out or in. And so the temperature of the water changes. Now, what's the advantage? Well, you can take items that don't burn easily and get them to burn in a bomb calorimeter. And actually, bomb calorimetry is how they measure the caloric content of food, because they put a little amount of whatever the food is into the bomb, and they fill it with oxygen, and it burns. And it's at really high pressure within the chamber but the volume can't expand, hence its constant volume. So in the case of the bomb, that is really how they use to determine how much caloric content is in your candy bar or your cookies. Things like Fritos will burn on their own. If you ever get stuck camping and you can't get the fire to start and you got Fritos, throw them in there, they burn. Nuts burn really, really, really well. Okay? So let's again talk about chemical reactions, because that's what we're going to do in the coffee cup. So with a chemical reaction, what you have is the reaction is going to take place there. So the reaction itself is the system. And the surroundings in this case will be the surroundings, will be the solution. So its surrounding is mostly water. So you can have real boundaries. So a glass of the beaker, the styrofoam of a cup, or you can make up an imaginary line. So we're talking about a line 200 nanometers from the surface. And you're like, really? Yeah. So when we talk about the system surroundings boundaries, they may be real, as in you do a chalk line, or they may be imaginary or designated like the other side of that door. So the door may be open, but it's got an imaginary border with it. Okay, so when we look at this, we can get these things together. So that brings us to what we're working with. Well, we're working with heat capacity. And just like certain things, there's a variety of ways to do it. The heat capacity is the energy required to raise the temperature of a sample by 1 degree C. Now, it's a function of the substance, the mass, etc. Because things like cork, wood, don't tend to transfer energy. Usually stir hot pots with a wooden spoon. Metals like stainless steel, etc., metal spoon, they will transfer heat. So that's the heat capacity. If you're talking about the specific heat capacity, it's the same thing, except you're specifying 1 gram of the sample by 1 degree. Okay, so heat capacity is a general, specific means 1 gram, and then molar heat capacity is 1 mole. So it's the amount of energy required to raise the temperature of 1 mole of a sample by 1 degree C. Now, they are all a function of the substance, the mass, etc. So you'll have to take that into consideration, but where do you get such values? Well, you can either determine them. So if you're given the energy transfer and the other information, except for the specific heat, you can calculate the specific heat, or you can look it up. Now, you can't look it up on a test, so I will be giving you specific heat, but here's some specific heat of some things in your text. Now, this is actually a boring table because it doesn't have that much. Notice it does have some metals over here and a liquid over here. There's water. There's kind of your base. Methane. So gases here, a solid here. So that can mean a variety of things. Now, here's the trick. And you're going to see this at least twice. But when we do the next step, we're going to talk about the temperature change. Now, we can either use Celsius or we can use Fahrenheit. No, can't use Fahrenheit. Fahrenheit's bad. Celsius or Kelvin, because they're both linear scales. So when you subtract the initial and the final, it's the same value. I'll walk you through one in just a second. So when we talk about this, we're talking about the calorimetry calculations. Well, here's your basic calorimetry. Q is the heat transferred. where M is the mass, specific heat is C sub S. I will often use specific heat for specific heat because not everybody uses the same symbol for it. And then delta T. Delta T final minus delta T initial. And on the next slide, I have a little more room, so I'll show you about this rule. That's basic calorimetry. If you're dealing with a bomb, then it's a little simpler. You still have delta T, but the mass and the specific heat have been combined into the heat capacity of the calorimeter. So you usually have a bomb heat capacity, which you have to determine by running a known sample. And delta T is still temperature final minus temperature initial. Both of these equations are on your formula sheet, so it's not like you have to memorize them. But I will warn you right now, and for some reason this happens in the gas chapter and carries through into this chapter, is people don't keep up with your units. And you remember, your units are your friends. They will tell you where to go, and they will tell you if you're right. So what are we going to do? Well, we're going to combine sample A with sample B. And when they're done, they will reach some equilibrium. Now, notice that when they combine and they're done, the temperature of A is equal to the temperature of B. It's the same at equilibrium. And equilibrium is when we have transferred all the energy, etc. And notice if you take 10 and 75, you get 85, and you divide it by 2, it's 40 something. It is not half. You really don't know what that final temperature is going to be without the specific heats. Now, I told you that I would show you the delta T value. Remember, it's T final minus T initial. Okay, so let's do it in degree C. So I'm going to use easy numbers. So T final is going to be 100 and T initial is 20 degree C. Okay, so delta T will be 100 minus 20, which is 80 degrees C. Everybody good so far? Well, let's do the same temperatures in Kelvin. That means the temperature final will be equal to 373.15. And temperature initial will be 293.15. And those are K. So delta T will be equal to 373.15 minus 293.15 K. Guess what? Comes out equal to 80 degrees. Whoops, 80 K. K doesn't get degrees. So the point being is it doesn't matter whether you're doing it in degree C or K. Just don't switch it in the middle, okay? So that brings us to the first problem. So what are we going to do? Well, a couple of y'all have expressed the point that sometimes it's hard to figure out what you're looking for. Okay, so these are word problems. Most people hate word problems. Word problems are not bad once you figure out how to take the pieces, parts you need, and ignore the rest. So we're going to be given 25.0 grams of ethylene glycol. And I'm going to call that ethyl gly. Okay, needs 90.7 joules to raise the temperature from, and the temperature change is going to go, we want delta T, which is T final, minus T initial. So from 23.7, that'd be your initial, to 25.2, that'll be your final. So first things first, we get 1.5 degrees C. Now let's go back and look at it. So grams of ethylene glycol, that's a mass. We don't have a full equation, so we're going to leave it alone. And we have 90.7 joules. So that's some form of energy. And remember, energy comes in Q and W. Well, we're not doing W, so that's going to be my Q value. So we are looking for the specific heat capacity, so that means that Q is going to be equal to the mass times the specific heat times delta T. It's a calorimetry problem. We plug in what we know. Okay, so this is 90.7 joules. Our mass is 25.0 grams. Our specific heat is what we don't know. And our delta T we've actually calculated is 1.5 degrees C. All right, so that means X is equal to 90.7 joules divided by 25.0 grams divided by 1.5 degrees C, which means when we do the math, we're going to end up with 2.41867 joules per gram per degree C. Because see, none of our units canceled. So we're using three significant figures, so it's 2.42 joules per gram per degree C. Oh wait, we're using two significant figures, so it'd be 2.4 joules per gram per degree C. Okay? Now, if I ask for three significant figures, it'd be this value here. So, the problem's not hard once you identify all the pieces parts. So, of course, let's do another one. If 58.3 grams of iron is warm from, what quantity of energy is transferred to heat the iron? Okay, so we're going to transfer energy. That means it's a Q problem. Q is going to be equal to mass times specific heat times delta T. So in this case, we're looking for Q. That's what we don't know. We're given our mass, which is 58.3 grams. We're given our specific heat, which is 0.449 joules per gram per degree C. And I like to do delta T off to the side. We're moving our final temperature. This is T final, and this is T initial. So it's 33.8 minus 22.3, which is 8 minus 5. So it's 11.5 degrees C. Okay, now, guys, real quick, this happens to be positive. Is it always going to be positive? No. If we had cooled it off, it would start at a higher temperature and go to a lower temperature, and we'll do one of those. So remember, the sign is strictly directionality. So it's 11.5 degrees C. So if you'll notice, the degrees C cancel, the grams cancel. So I'm left with joules, and when I do the math, I get 301.03205 joules, which, if we want to convert it to kilojoules, we can. We don't have to. We have three significant figures, so it's 301 joules. If you wanted it, it'd be 301 kilojoules. Doesn't matter. Again, watch out for D2L or whatever, and when I specify. Okay? So, you're like, oh, these are kind of fun. Okay. Actually, they are kind of fun. I enjoy these problems, but we're about to get into the ugly A word. Now, a 55-gram piece of iron is heated and then plunged into a beaker of water. The beaker holds how much water, temperature, whatever. Okay. What is the temperature of both the water and the piece of iron? Well, something I forgot to give you is that water, I gave you the specific heat of iron, but water is 4.184 joules per gram per degree C. Okay. Now, Wow. Okay, this actually is not a bad problem. What we've got is the Q of the iron is equal to the negative Q of the water. Now, does the water have to get the negative? No. I could have easily said the negative Q of iron is equal to the positive Q of water. The signs have to be opposite. That's all that counts. And is one of them going to come out negative and one of them going to come out? Yeah. But does it matter? No. Signs have to be opposite. Okay, so there are a couple ways to do this. I'm going to work off to the side first. I'm strictly going to set up the Q of iron over here. So the Q of iron, and remember, Q is equal to mass times specific heat times delta T. All right, so we have our mass. It's 55.0 grams of iron. We have our specific heat, which is 0.449 joules per gram per degree C. And then we have our delta T. And we're told that initially you're heating it to 425 degrees C and then plunging into water. Now, when you're done, first things first, remember the temperature of the water is going to have to equal the temperature of the iron. Okay? So temperature final will be the same for both. So T final will be the same for both. Okay? We remember that. And delta T is always T final minus T initial. So our initial we don't know. So we're going to call it T minus our initial temperature, which is 425 degrees. Okay? All right, now the Q of water. We're told we have 600 mLs. And remember that this density of water is 1, so that means we're going to have 600 grams. And we're given the specific heat of water, which is 4.184 joules per gram per degree C. And our temperature final will be the same, but our initial temperature is going to be the 25 degrees C. Now, we have identified both of them, but now we have to plug them in. So, again, it doesn't matter who gets the negative. And this one I designated the water to get the negative, but it really doesn't matter. So I'm going to set up Q of iron is equal to minus Q of water. Now, that's a straight thing, and I want you to look at it. So we're just going to set it equal. So 55.0 grams times 0.0, whoops. See, I can't even copy. The problem on this one, honest to goodness, is you get lost in the algebra. And T minus 425 degrees C is equal to negative, and do not forget that negative, I'm going to run out of room. 600 grams times 4.184 joules per gram per degree C times T minus 25 degrees C. All right, now, if you've heard the phrase, there's more than one way to skin a cat. No, you're not skinning the little fuzzy critters that meow. I grew up on the Gulf Coast, and I never understood more than one way to skin a cat until I moved to North Georgia. And we were going fishing, and we fished for catfish. And my friend was like, now we have to skin it. And I'm like, what? You skin catfish. So everybody has their own technique. The only thing about this problem from this point on is you must obey the rules of mathematics. I'm going to do it my way. Some of you are going to follow me. Other ones are going to go, I don't want to do that way. It doesn't matter as long as you obey the rules of mathematics. So, what I would do is combine. So, I'm going to get 24.695 T final minus 425 is equal to negative 2510.4 times T final minus 25 degrees C. Everybody's usually with me to this step, and then this is where it gets ugly. So then what I'm going to do is divide both sides by 24.695. So I get T final minus 425 is equal to negative 101.6562057. Do you need to keep that many digits? No, I let the calculator carry them, so it's going to carry more. Okay, now you're going to distribute, so T final minus 425 is going to be equal to negative 101.6562057. T final plus 2541.405143. Wait, how do I get the plus? Because the negative times a negative is a positive. Okay, because what you're doing is you're multiplying. So then what I will do is move this to this side. So plus 101.6562057. T final is 101.625. No, 656. 2057 TF. So we end up with 102.6562057 T final. And I move the plus 25 to the other side. So I end up with 2966.40514, which means I divide both sides by 102, so the T final comes out equal to 28.8965 degrees C. And if I'm using three significant figures, it's 28.9 degrees C. It's my final answer, and that would be T final. Now, the beauty or ugliness of this is you can check it. So if I plug it back in using the T final as 28.9 degrees C, then the Q of iron, I end up with negative 9781.69, and the Q of water is equal to positive 979056. Now, are they identical? No, but they're pretty darn close. And the closeness, not the identical part, well, the identical part, is a function of how much you round. So the less you round, so if we had taken this out to 4 significant digits, it would have been closer, 5 even closer. So this actually comes down to the rounding rule. Okay? Now, you will tend to have a problem like this on the exam that you will be asked to work and show me the work. And again, it's not difficult. The algebra gets a little wonky, but you need to show me your work. And this is why submitting your work after the exam is critical. All right, variation on a theme. We did the first one with a coffee cup calorimeter. This one's going to use a bomb. How do you know it's going to use a bomb? It will say bomb somewhere in it. Okay, so remember the Q of a bomb is equal to the calorimeter constant times delta T. Okay, so if we start there, that's the equation we're going to do. We know that it has a heat capacity of 1.56 kilojoules per degree C. Oh, and that's the other thing. The bomb tends to be higher energy, so it's in kilojoules. All right, so delta T, remember, is T final minus T initial. So the final temperature was 29.9. The initial temperature was 26.7. That means our delta comes out equal to 3.2 degrees C. All right. So the question that's asked is calculate the energy of combustion of quinone per gram and per mole. Okay. So we're going to start with Q of the bomb is equal to minus Q of the reaction. Okay. So we're comparing one to the other. So let's solve for the bomb first. So Q of the bomb is equal to 1.56 kilojoules per degree C times 3.2 degrees C, which means our bomb comes out equal to 4992 kilojoules. And it's positive. But the bomb is absorbing whatever is given off. So if the bomb goes up in temperature, it's absorbing heat. If it goes down in temperature, it's losing heat. So that means the Q of the bomb may be plus 4992 kilojoules, but the reaction is got a negative Q, so the Q of the reaction has got to be negative 4992 kilojoules. So the reaction energy is that. But we're asked to calculate the energy of combustion of quinone per gram. So if it's kilojoules per gram, then we start with our kilojoules, which happen to be negative because it's an exothermic, and we're going to divide it by the grams. Well, we're given 1.964 grams. So we do the math, and we get negative 25.417 kilojoules per gram. Now, I did not use significant figures here. Let's assume we're going to use 3. So at this point, we would be negative 5.4 kilojoules per gram. All right. Then the question was how many kilojoules per mole? Well, we could actually go back and take and figure out the moles by starting with our grams, which is 0.1964, and use the molecular weight, this molecule, 1.809652 grams per 1 mole. Or, if we're doing it in kilojoules per mole, we could start with the negative 25.4 kilojoules per 1 gram. And we know that there are 108.09, if I could read this, 09652 grams per 1 mole. My grams would cancel, and I'm left with a whopping negative 2747.49 kilojoules per mole, which again, 3 significant figures would be negative 2750 kilojoules per mole, which makes sense because you're like, wait, that's huge. Yeah, it is huge because look at how much you're getting per 1 gram. And you got 108 grams in this compound, so it is got a whole lot more weight than the other one did. Okay, so this is actually critical when you're talking about regulation of body temperature. So this is actually one of those cool ones to read. Some of them are more interesting than others, not going to lie. But this one actually is kind of interesting because this one relates how your body temperature regulates to calorimetry.